Okay, next we're going to look at some very special triangles that we might look at. And the first one we're going to look at is an isosceles right triangle. So notice that if it's isosceles, remember we've studied about isosceles triangles. We know that isosceles triangles have a pair of congruent sides. So let's let both of these sides be x. So y and x are the same thing in this case. And then the hypotenuse, we'll call that r as usual. Now notice then that the three angles altogether add up to be 180 degrees, or pi radians. But if it's a right triangle, which we have a right angle here at B, okay, right angle right here, then that takes up half of the amount of the interior angles just by itself. So that leaves exactly 90 degrees, or pi over 2 radians, for the other two angles for any right triangle. So in a right triangle, the two angles the two acute angles are always complementary. They always add up to pi over 2 radians, or 90 degrees. So if it's an isosceles triangle, not only are the two sides congruent, but those two acute angles are also congruent. So what this tells us is that when you take that pi over 2 and divide it by 2 again, we get pi over 4 for both of these angles, or in degrees, that 90 degrees is spread evenly among the two angles, between the two angles, for 45 degrees. So this is a 45 degree, 45 degree, 90 degree triangle, or pi over 4, pi over 4, pi over 2 radian triangle. Okay? Now, remember that we can draw any such triangle, and we have this relationship x, x, and r for the sides. So by the Pythagorean Theorem, r squared equals x squared plus x squared, because a and b are both x and c is r from our normal labeling. So we have right here, you can see r squared equals x squared plus x squared. But x squared plus x squared is 2x squared. So to solve for r, we take the square root of both sides, and we get r is the square root of 2x squared. The square root of x squared is the absolute value of x, but x is a length, so that's x. And so the r is the square root of 2 times x. So we can pick any length we want for x here, and once we pick that, it can be anything we want here, but once we pick that length, then we know the other side is also x, the other leg, and the radius is square root of 2 times that x. So the sides are in the ratio 1, 1, square root of 2. And so we can compute the trig ratios from this. So in fact, we can actually pick one where x is 1 for one example. So the sides then are actually 1, 1, and square root of 2. So now we can find the sine, cosine, and tangent of pi over 4 exactly from this triangle. So sine, so if you think of this as the 45 degree angle down here, that it's opposite over hypotenuse, that's 1 over square root of 2. Some people like to have their fractions with rationalized denominators, so if we multiply top and bottom by square root of 2, in the numerator 1 times square root of 2 is square root of 2, and the denominator square root of 2 times square root of 2 is just 2. So we can think of the cosine of pi over 4 as being 1 over square root of 2, or square root of 2 over 2. That's pi over 4 radians, of course. We could also say it in degrees. Cosine of 45 degrees is 1 over square root of 2, or square root of 2 over 2. Either one of those is equally good as far as I'm concerned. Now the sine of 45 degrees, we take the same one. That was the sine, opposite over hypotenuse, but it's also the cosine because it's adjacent over hypotenuse, but the opposite adjacent are the same. So in this case, the cosine and the sine are the same. Cosine of pi over 4 is 1 over square root of 2. Sine of pi over 4 is also 1 over square root of 2. And the tangent of pi over 4 is x over x, or 1 over 1, which is 1. So the tangent of pi over 4 is 1. The tangent of 45 degrees is 1. And so these have some nice things, and we don't have to do this by using either a measurement or a calculator to figure these out. These we can know exactly what they are, even though the cosine and sine are irrational numbers. we can see what that is. So that comes from a right isosceles triangle, a 45 degree, 45 degree, 90 degree triangle. The next thing I'm going to look at is start with an equilateral triangle. Well, an equilateral triangle is not a right triangle, okay? But let's let the side be 2x. And then what we're going to do is we're going to split it down the middle. So we draw a point from D to the midpoint of the other side, and that turns out to be a right angle right there. And we're going to work out, and we'll call A the altitude here, or the height of the triangle A. And then B will be x here, which is half of a side of the original equilateral triangle, and this side over here is 2x. So this line segment here is an angle bisector at the top. So remember, in a equilateral triangle, all the angles are 60 degrees. So this little angle up here at D is half of that, or 30 degrees. Or in radians, this one down here is pi over 3, and this one up here is pi over 6, half of that. Okay? And so this triangle right here is actually a right triangle, so we can start talking about sine, cosine, tangent of this angle here, which is pi over 3 radians, or 60 degrees. And we can also talk about sine, cosine, and tangent of this one up here, which is 30 degrees, or pi over 6 in radians. Now, let's see what we've got. We've got A, x, and 2x. Okay? So, how are we going to figure out what this is? Well, let's use the Pythagorean Theorem again, because this is a right triangle after all. So we've got a squared plus x squared equals 2x quantity squared, like that. Well, 2x quantity squared is 4x squared. Subtract x squared from both sides to get the x's together, and we get a squared equals 3x squared. Then take the square root of both sides, and we see a is the square root of 3x squared. And so that's the square root of 3 times the square root of x squared. Square root of x squared is absolute value of x, which is just x, since x is a positive value. And so we get a is the square root of 3 times the x. So these are in the ratio, whatever this is for x, this one is square root of 3 times that x, and the hypotenuse is twice that. So when you have a 30 degree, 60 degree, 90 degree triangle, remember the shorter side is opposite the 30 degrees, the longer leg is opposite the 60 degrees, and of course the longest one, the hypotenuse, is opposite the 90 degree angle. And whatever that shorter one is, we can base everything on its length. If that's x, then the longer side is square root of 3 times that x, and the longest side, the hypotenuse, is twice the x. Well, so for one thing, you could just let this bottom one be 1, and this would be square root of 3, and this would be 2, and we can use that to find the sine and cosine and tangent of these. So cosine of pi over 6, in other words, cosine of 30 degrees, so we're looking at, for 30 degrees, this is our angle up to the top. Okay? And we have cosine would be adjacent over hypotenuse. So adjacent would be this one, hypotenuse would be this one. So square root of 3 times x over 2 times x, the x's cancel, and we get square root of 3 over 2. The sine of pi over 6, or sine of 30 degrees, again, this is the 30 degrees, or pi over 6, the smaller of the three angles. And that's going to be opposite over adjacent, opposite over hypotenuse, excuse me. Sine is opposite over hypotenuse. So that would be x over 2x, that's 1/2. So the sine of 30 degrees is exactly 1/2. The tangent of 30 degrees, or in other words, the tangent of pi over 6 radians, then would be opposite over adjacent. That would be x over square root of 3x, that's 1 over square root of 3, which could also be written as square root of 3 over 3 if you like to rationalize the denominator. Now it's interesting that there's a reason why this is called cosine. It's the sine of the complementary angle. Look what happens. The 60 degrees is complementary with the 30 degrees. So the sine of the 30 degrees is the cosine of the 60 degrees. See how these match up this way? So notice that's going to be true in a right triangle. Whatever your cosine here, adjacent over hypotenuse, if you do the same ratio based on the other angle, that's opposite over hypotenuse. So it turns out that the cosine of one of the angles is the same as the sine of the other within a single triangle, and vice versa. So this time the cosine of 30 degrees was square root of 3 over 2. So the sine of 60 degrees is also square root of 3 over 2. The sine of 30 degrees is 1/2, so the cosine of 60 degrees is 1/2. Now the tangents turn out to be reciprocals of each other. So the tangent of 30 degrees again was opposite over adjacent. X over square root of 3 times x is 1 over square root of 3, whereas the tangent of 60 degrees opposite over adjacent leg, that's a over x, that's square root of 3x over x. The x's cancel and you get just square root of 3. So let's summarize this. And so here are our two special triangles, and these are drawn to scale. So I've chosen, rather than memorizing all that stuff that I just said, all you really have to do is just memorize these two pictures. Okay? And you do want to memorize this because we'll be using these triangles quite a bit in this class. So here are the two triangles, and they're drawn to scale so that this is one length here. This is isosceles, so the other is the same length here, and this is the same one here. So I chose one for the shortest side in all the cases. And so in the case of the isosceles triangle, where both angles are pi over 4, and 90 and pi over 2 for the right angle, or in degrees, 45 degrees, 45 degrees, 90 degrees, then the hypotenuse is just square root of 2 if these sides are 1. So just memorize this. When you got a 45 degree angle, the sides are 1, 1, and square root of 2. And then for the 30 degree, 60 degree, 90 degree triangle, remember that the shorter side is the one that's going to be 1. The longer side is square root of 3, which by the way is noticed is longer than the square root of 2 here. This is to scale, and 2 of course is the longest of the numbers we have here, the biggest number, the longest side, and so that's 2 there. And so you label the sides 1, square root of 3, and 2. And of course the one opposite the 30 degrees is the 1, the shortest one. The opposite the 60 degrees is the square root of 3, and of course the longest side is the biggest number, which is 2. And so just memorize that. And if you've got that memorized, then from this you can easily read off sine, cosine, and tangent. So if we want to find the cosine of 45 degrees, remember it's just, there's your angle, you just do adjacent over hypotenuse. If you want to find sine, it's opposite over hypotenuse. If you want to find tangent, it's opposite over adjacent. Pretty easy. For pi over 3, remember this one's opposite, this one's adjacent, so square root of 3 over 1 is the tangent. Opposite over hypotenuse is square root of 3 over 2 for sine, and adjacent over hypotenuse is 1/2 for cosine. If you're using the 30 degree angle up here, then this time the square root of 3 is adjacent, and you put that over 2 for the cosine, and you do opposite over hypotenuse 1/2 for sine, and you do opposite over adjacent leg for tangent, which is 1 over square root of 3. So you can just get everything just from this, these pictures here. Okay, but notice they have different lengths for the for everything except for the red lengths. The red lengths are all 1, so we sort of specify the shortest side to be 1 and then base everything on that as a multiple. So you want to memorize not only the definitions of the trig functions, but then memorize these two pictures so that you can quickly compute exact values for trig functions of these angles. And we use these a lot, not because they're particularly important in and of themselves, but they give us some easy ways to find exact answers for certain trig functions of certain angles that we normally would not be able to figure out exactly.